Hi guys, sorry I can't be there today, so I wanted to finish up the notes real quickly, and then you can have the rest of the time to work on the homework, and then we'll go over it tomorrow before we finish up our notes in chapter 20 on a little more complicated redox reactions. So as we kind of talked about on Monday before we ran out of time, single replacement reactions are also redox reactions. And we started with the problem, I don't know why this is blurry, zinc reacting with hydrobromic acid. So here's our, yikes, why is that so, trying to get that so it's not so blurry. I don't know, it's not getting better, so I apologize, not sure what the deal is. But here's our balanced molecular equation that we are used to doing. And so what we want to do is go through and assign oxidation numbers like we did earlier in the notes. So that would give zinc being in its elemental state, an oxidation state of 0. And then hydrogen would be a +1. That would make bromine a -1 because together hydrobromic acid is neutral. And then on the product side, the zinc would have a +2 charge because you can see that it crisscrossed a 2 with bromine. And with, again, being zinc bromide being neutral, and we have 2 bromines, each bromine would have a oxidation state of -1. And then hydrogen gas, H2, being its normal elemental state, it would have an oxidation state of 0. So obviously the bromine is not changing its oxidation number, so that is just a spectator ion. And then we can look at the element that is losing electrons would be our oxidation reaction. That would be zinc. Zinc going from its neutral element to a +2 ion. It lost 2 electrons. So we write the oxidation reaction as follows. Zinc going to zinc +2 plus 2 electrons. And as you notice, both sides of the arrow are not only balanced element-wise, but also balanced in overall charge. So we have neutral on the left side, and then we have a +2 and a -2 on the right side, so the charges are balanced as well. And then hydrogen would be our reduction reaction, because hydrogen on the reactant side is going from a +1, and there happens to be 2 of them. So each hydrogen is gaining an electron, so it's gaining a total of 2 electrons. So we show gaining electrons by writing it on the reactant side and then forming hydrogen gas H2. And again, not only are the elements balanced, but our overall charge on both sides is balanced. Now in this case, zinc is losing 2 electrons, hydrogen is gaining a total of 2 electrons. So we don't have to balance anything electron-wise. Those are already balanced. So when we combine these together in our overall redox or net ionic equation, the only thing that cancels out is our electrons, and that gives us our overall zinc +2 hydrogen ions forming hydrogen gas and zinc +2. So that is our balanced redox reaction. Then another example, manganese metal reacting with lead 2 nitrate. Same thing, we write out our balanced molecular equation that we're used to doing. Manganese reacting with lead 2 nitrate forming, so the lead and the manganese will trade places, and we'll get manganese 2 nitrate and plain old lead metal. Then going through and assigning oxidation numbers to see which elements are gaining and which elements are losing electrons. The manganese in its elemental state is 0. The lead, based on our crisscrossing, is +2. Then nitrogen, again looking at the polyatomic ion, knowing that it has to have an overall -1 charge. Oxygen would be a -2, and there's 3 of them, so that gives us -6 total, which would make nitrogen +5. Then over on the product side, manganese now is a +2, as we can see from our crisscrossing. The nitrogen and oxygen, their charges or oxidation numbers are still the same. And then lead in its elemental form has an oxidation state of 0. So again, looking at the element that has lost electrons and has undergone oxidation. That would be the manganese, going from Mn to Mn plus 2. So again, it's losing 2 electrons, and our charges and element are balanced. And then our reduction reaction would be the lead, going from lead plus 2, gaining 2 electrons to form lead metal. And again, in this case, the electrons are already balanced, so when we combine them, we don't have to do anything else. We can just combine the two together, the electrons cancel, and our overall net ionic or redox reaction is manganese plus lead plus 2, forming lead plus manganese plus 2. And again, in honors chemistry, we looked at the activity series, kind of just, gave you the chart and said top of the chart are the more active metals. As we go down the chart, they're the less active metals. There's a table on table 4.5 in your book that gives you the order. You don't have to memorize this order, but just obviously, as we've talked already about periodic trends and stuff, the more active metals are going to be your alkali metals on the far left-hand bottom corner of your periodic table. And as we go towards the right side of the periodic table, the metals get less active. What this is really showing is how easily metals are being oxidized, because again, oxidation is losing electrons, and that's what we said ionization energy is doing, is how easily metals can lose electrons. So the more easily metals can be oxidized or lose electrons, the more reactive they are, and more easily they will form compounds. So again, the group 1As are at the top for the most part. They are the most active because of their low ionization energy. They will undergo oxidation most easily. Transition metals tend to be towards the bottom. They are the least active. That's why we use them more in jewelry and household things and stuff like that, because they're less likely to react with other stuff. And again, the rules of the activity series, only a more reactive metal will react with a metal in a compound, so we always want the more active metal will replace the less active metal in the compound. In terms of a metal being able to react with an acid, it has to be above hydrogen, so down about 3/4, 2/3 of the way down the activity series, you'll see hydrogen. Obviously, hydrogen's not a metal, but that's just put in there to show you any metal above hydrogen will react with an acid and replace the hydrogen in the acid to form a new compound and hydrogen gas. And then the very top part of the activity series, the group 1As and some of the more active group 2As, so anything sodium and above will react with water and form hydrogen gas as well, metallic hydroxide and hydrogen gas. And again, it's sodium and above will react with water. Anything below that will not. And then these are not obviously metals, but the halogens have an activity series as well based on their tendency to gain electrons or be reduced. And fluorine is at the top of the chart. Fluorine is the most active halogen, followed by chlorine, then bromine, then iodine. So they go in the order that they are located on the periodic table. And again, that is due to their electron affinity and the ease at which they will gain electrons and more likely be reduced. Now, there are other types of redox reactions. Again, in chapter 20 tomorrow, we'll take a look at some more complicated redox reactions, but there are other simple types of redox reactions, like combustion reactions. Combustion reactions are usually redox reactions, and one way to spot something that's a redox reaction is usually if you have elements in their elemental form on one side of the reaction And in a compound and on the other side of the reaction, that means they're either gaining or losing electrons. So that's a good sign that that's a redox reaction. And then, again, like we talked about at the beginning of these notes, a lot of the synthesis reactions, especially where we are taking just two elements and forming a compound, obviously they're gaining and losing electrons to form that ionic compound. So those are some other types of redox reactions. So hopefully now you can finish up your your worksheet, and we'll take a quick look at that tomorrow before we continue on with some more complex redox reactions in chapter 20. Shoot me an email if you have any questions, and I will see you tomorrow. Bye.